I'm Baland Omar. I'm going to give you this course on group theory. We will start by defining some things, and as we're defining things, we're going to be building blocks until we reach what a group is. So group theory is about, it's about groups, it's about structures, it's about symmetries, and I'm sounding a bit too vague right now, but the reason is because the only way for me to be more clear if we formally, properly introduce the definitions for a group. But to reach the notion of a group, we need to construct it little by little. So in this lesson here, I'm planning on making a series of lessons on group theory. And the first lesson is just constructing a group, saying what a group is. So these are the following topics. The first thing we're going to start with is a set. I'm sure you've all known what a set is. It's a collection of elements, right? So let's call S some set, and we will define a binary operation, and I will be defining that in a minute. And on that binary operation, we will explore what it means to be associative, what it means to be commutative. Then we will introduce what is called the neutral element, and then a demi-group, then an inverse, and then a monoid, and so on, so forth, until we reach the notion of a group. Let's get started. So right here, we have our first definition of this course. I'll be calling it def, as in definition. So let S be a set. We call a binary operation. So a binary operation, I like to give it a symbol, star, is a mapping or an application So as you know, an application is a function that takes some certain element and gives you back another element. So it takes an input and gives you an output. So it's a very formal way of defining what an operation is. And I will be explaining this formal way right now. So a mapping that takes an element from, so the mapping is called star. It takes an element from S cross S and gives you S. So it takes two elements A and B from S and it gives you back an output of A star B. So this star is the exact operation we're defining here. A quick example to make all this clearer is addition. So if we have two numbers, 2 and 3, if we apply the operation of addition on them, so 2 plus 3, we get another element, which is also a number, which is 5. So 5 here is your A star B. I need you to think about these things as we move on. But I also need you to not forget that this is any binary operation and not necessarily addition. It could be multiplication. It could be matrix multiplication. It could be any type of operation that takes in two elements and gives you another element inside the set S, inside the set. Because if it takes you out of the set S, then we have a problem. It's not a binary operation anymore. So an example of an operation that is not a binary operation is, for example, let's take the set of z bigger than 0. So these are just the natural numbers 1, 2, 3, 4, etc. All the positive numbers. And let us define the operation to be subtraction. Another way to write this is to say z bigger than 0 paired up with the operation. Instead of star, I will write minus, the usual subtraction that we're all used to. So is this a binary operation? I'll give you a second to think about it. But the answer is no, because if you take an element 2 and an element 3 and you apply 2 minus 3, you get minus 1. And minus 1 is not an element of z bigger than 0. So this operation takes you out of the set z0 bigger than 0. In other words, it is not closed under the operation. So it is not a binary operation. Okay, now good. Now that we have defined what a binary operation is, let's briefly define what it means to be associative. Associative is, as you know, something that if you have 3 elements, so if you write down A star B and the product of A and B, you apply it with C, it would give the same result as if you would have A star the product of B and C. So again, here we apply A and B together in the operation, and then their product we apply it to C, and over on the right side we apply B and C together, and whatever the product of that is, we apply it to A. And associativity tells us that these two give the same result. For all, the symbol means for all A, B, C in our set S. This means it is associative. Well, what is associative? The operation star. Star is associative if this property is true for all the elements in our set S. Now let's give an example on when is it true and when is it not true, so that's a bit clearer. So let's take the set Z and plus. So Z plus is the set of all the integers, -2, -1, 0, 1, 2, and so on, with the operation plus. It's associative, so plus is associative. Because addition is known to be associative. We already know that. We know that addition is associative. Great. However, let us consider now z only greater than 0 with the operation minus. Let's take 1, 2, 3, and the operation being minus. So is this associative? Not quite, because 3 minus 1 minus 2, no, apologies. I will change a bit my example. I will give even a better example than that. So let us give z, all of z, with the minus operation. So minus here is not associative because if we take the example of 1 minus 2 minus 3, so we apply the subtraction on 2 and 3, and then we apply 1 minus that, we get back 2. However, if we change the order of applying the operation, 1 minus 2 and then minus 3, you get back something that is not quite equal. You get back minus 1 minus 3 is minus 1 minus 3 is minus 4, which are not equal. That means it's not associative. A definition, one of the things on our topic. So S with, not plus, with the operation star is called a demi-group if star is associative. So all it takes for S star to be a demi-group is for star to be associative. Well, star has to be a binary operation, but that is always going to be the case from now on. It is just going to be the case. So we have that it's a demi-group. So that's our first bit of structure that we're giving our operation on the set. Now, let us define more structure on our operation. So the structure I want to give now is commutative structure. So if x star y is equal to y star x for all x, y, and s, then we call star commutative. We've all heard of addition being commutative, multiplication being commutative, but is there some operation that is not commutative? Yes, there is. It is the matrix multiplication. That is not commutative. If you multiply a matrix from the right or from the left, you would get two different matrices, two different results. It is a binary operation, and it is associative, but it is not commutative. Now, let us add even more structure, providing yet another definition that relates to our binary operation. An element X in S is called a neutral element, and we will see in a second why the name is neutral element, if for all y in S, x star y and y star x is equal to y. So, vaguely speaking, this element, if you apply it to any y, any element y in S, it would just give you back y itself. So it has absolutely no effect on any of the elements in your set S. What is a good example of that? Well, we know that in our integers, z greater than 0, well, greater than 0 being natural numbers now, and the operation being addition. So in this structure here, the neutral element would be the neutral element is 0. And why is that? Because simply put, 0 plus any integer, let's say 5, is equal to just 5. And 5 plus 0 is also equal to 5. So 0, with the operation of addition, has no effect on any integer in the set, or any natural number in this set. So we call 0 a neutral element. In fact, it is the neutral element. And I will explain in a bit what the difference is between calling it a neutral element and the neutral element. In fact, we will prove now that the neutral element is unique. That means there is only one neutral element in our set. There cannot be two different neutral elements. Let us prove that. That is our first, we call it lemma. If there is a neutral element, if it exists, it is unique. Okay, so what is the proof of that statement? How do I prove that it's true? If I want to show that the neutral element is unique, then I want to show that there cannot be two different neutral elements. So if we had x and y and S, my set, such that x and y are neutral elements, I want to be able to prove that x is equal to y, thereby letting me say that there is only, in fact, one neutral element. Because if I have two, I want to be able to prove that they're equal to each other, giving me only one neutral element. So since X is a neutral element, that means that X star any element in the set gives me that element. In particular, X star Y gives me Y, because X is a neutral element. I will use the same logic, but with Y now, separately. Since Y is a neutral element, X star Y gives me X, because Y is a neutral element now. But we just said that X star Y is Y, and the same thing is equal to X. So by transitivity, X must be equal to Y. So that means there is only one unique neutral element in my set X, thereby ending the proof of this lemma. All right, let us define what a monoid is. A monoid is a set that has a binary operation with a neutral element and star is associative. In other words, all what I've done is I've added one more structure to what a demi-group is. A demi-group being a set within a binary operation that is associative. A monoid is all of that plus the existence of a neutral element. For example, the set Z greater than or equal to 0 with addition is a monoid. We've already established that 0 is a neutral element for the integers, and Z bigger than or equal to 0 contains 0. So it is in fact a monoid. However, Z bigger than strictly than 0 with plus is not a monoid. Because there is no element in Z bigger than 0 that acts as a neutral element to all of the other elements in the set. So it is not a monoid. For it to be a monoid with addition, 0 has to be inside the set. Great. We have covered what a binary operation is. We have covered what a demi-group is with associativity. We have covered what a monoid is, adding a neutral element. And now it's time to add the last piece of the ingredients to have a group. This piece is called having an inverse. Definition: let S with the operation be a monoid. So already associative, already star is a binary operation, and it has an inverse. It has a neutral element. So let S star be a monoid. That's what I mean by saying it's a monoid. We define, let X and Y be in S, two elements, and let E be the neutral element. We say that Y is the inverse of X if X star Y gives me the neutral element E, and Y star X also gives me the neutral element E. I have to define both of these because I do not know for sure if my monoid is commutative. I don't know that if I can switch my order, it's going to give the same result. So I need to say X star Y is the neutral element and Y star X is the neutral element, E. And I call it, in this case, I call Y to be the inverse of X. I denoted X to the minus half. Keep in mind, even though this symbol looks familiar like that, that is absolutely not what this means. It just is a convenient notation given for what we call an inverse of X. An inverse of X being the element that satisfies these equalities. So in practice, what is a good example for this? Well, in Z with plus, the operation being addition, the inverse of 5 is minus 5. It's kind of weird to say that the inverse of 5 is minus 5. We're always used to calling the reciprocal of 5 the inverse, which is 1 over 5. But you have to keep in mind that the operation here is addition, not multiplication. And in addition, we have established that the neutral element is 0. So since by definition 5 plus minus 5 gives the neutral element and minus 5 plus 5 gives the neutral element, then the inverse of 5 is minus 5 because it satisfies the definition of what an inverse is. So in group theory, it's very important to stick to your definitions. Really study them and figure out why they are defined that way. So you need to forget about things that you've already taken, and you need to start thinking abstractly here. In this sense, we have forgotten what multiplication is in this set. We only know addition. We do not know subtraction neither. I have not defined subtraction. All what I know is there is a 5 and there is a 0, which is the neutral element, and I'm trying to figure out what is the element that if I add it to 5, I get 0. And that will be exactly -5. And as it turns out, adding the inverses to my monoid will give me a group. So this makes us ready for the last definition of what a group is. So let us lay the groundwork first. Let G be a set and star be a binary operation. We call the pair G star a group if, first of all, since star is a binary operation, we already know that star will take two elements from the set G and gives an element which is also in G. So that is done. However, that is something that you need to verify, first of all. You need to verify that star is a binary operation. And once that's done, you need to verify that star is associative. That is A star B, and the product of that, star C, is equal to A star the product of B and C with the operation for all A, B, C in your set G. Number 2, there exists, I like to use the symbol for there exists as the backwards E. There exists a neutral element. So my set G is actually a demi-group and it's a monoid. There exists a neutral element E such that E star X is equal to X star E is equal to X for all X and G. That is the definition of a neutral element. Third of all, and lastly, for all A and G, for any element A and G, there exists a B in G such that B is the inverse of A. What does that mean? That is, A operating with B gives you the element E, which is the neutral element, and B operating on A also gives the neutral element. Again, you might ask me, why do I need to verify both of these conditions? And I say, this is even if my group G is not commutative, but these two things have to be equal, even if it's not commutative. So this is the definition of what a group is. Notice that we started with a set, just a collection of elements, absolutely no structure at all. And then we have added an operation. Now there is a way for the elements to interact with each other. But interacting with each other also has some limitations now. We have added associativity. We have added a neutral element, something that has no effect on other elements. And now we're adding an inverse, which gives us back the neutral element from any element in the group. And we will discover in the future that just these simple properties will give us so much information about so many things in group theory and in other areas of mathematics. So this is the end of the lecture. I hope that you have enjoyed this lecture, and I will be continuing this series on group theory. Have a nice day. Bye.